and so on. Thank you, everybody. Remember that your experience in this session is dependent on the quality of your internet connection. And no matter what that internet service provider tells you about how great and how fast and wonderful your internet is, it may not be wonderful at this moment in time, which is going to cause problems with your experience here today. So if you have any issues, we recommend to you that you just log out of the session and come right back in. That will oftentimes fix it, and hopefully your bandwidth will correct itself and you'll end up with a good show. One other thing I have to mention is certificates of attendance. You do receive one for being a live attendee of this session, okay? Now that certificate of attendance comes to you by email, and it will bear the name that you entered upon registration. If you fat-fingered something when you registered, that's the way your name is going to be spelled. We at ASD do not touch the data. We don't manipulate it. We don't do anything with it. It's all done automatically off of our webinar platform. Now the same thing holds true for your email address. What you entered is the address that it's going to go to. So if it wasn't accurate, it's going to go off into space somewhere and it's going to bounce and it's not going to get to your inbox. And that's a totally automatic process, and based on, you know, your programming it essentially of your email address and your name. Now allow us a week to get that to you, and there will be that link to that certificate. But that email is important for a second reason, and that is that it will include a link to the recording of this session. So if you want to go back and review anything, and given by the complexity and details that will be covered in today's session, you'll probably want to go back and do that. And now without further ado, we are now going to go over to James Wilson with ATEC Training. James, over to you.
Okay, you got me there we go. Okay, good. All right, can we show my screen there? Everybody see that?
You're good to go.
All right. Well, we're going to have a little fun with it this afternoon. The biggest thing about it is when I say critical skills, I've been teaching electrical for better than 25, 30 years and having always fun. I'm the old timer. We call me the elder of the group of my friends right now. So we're looking at some of the stuff we look at. We got some class objectives. We're going to do a little Ohm's Law review. I know a lot of you guys say, I don't want to use that because I don't use it as practical. You use it every day. You just don't realize you do. We're going to talk about series circuit diagnostics, identifying and diagnosing parallel circuits, and identifying and diagnosing series parallel circuits. You can already see that if we teach you how to do a series circuit and a parallel circuit, you can diagnose series parallel. Why you need to understand the type of circuit you're on. So if you're looking at a circuit, if you're trying to repair something on a car, it's always a good idea to get a wiring diagram out and follow the circuit. The other thing I hammer to everybody every time is you have to check the power and the ground side of the circuit. If you have, and you also want to, if you have a 3-wire circuit like a sensor, you're going to have to check power, ground, and signal output. So there's some things up here. What really is a voltage drop? I think a lot of people have a hard time understanding what a voltage drop is, and we're going to try to make it a little bit clearer for you to go as and use it every day as a diagnostic tool. So one of the other things I looked at is I just added a few things from, I've done this once before this class, but I wanted to add a few things. Skills for techs are things we would like to know, or things we don't care to know, and there's always something you don't care to work on. Some of them show up in the bay you don't want to work on. And then there's critical skills that we need to know. And if you look at it, understanding electrical testing is a critical skill that all techs need. If you understand how the electrical circuit works and you understand how to use your scan tool together as a partner, you use the two together, because you have to remember that your scan tool lies to you a lot. Some of the data that you get on your scan tool is incorrect, or the company that manufactures the car decides to put in sensor data that is not there. It's just a substitute sensor data, not really the one you're looking at on the circuit. The other thing to keep in mind, we have a short period of time in class, and we're going to maybe go over some new things for some of you and a review to others. Now, this is what showed up on my nice little bay this week. It's one of the 3 that showed up that I thought like I'll get out. So I've got a 2012 Fusion. If you notice, I have a U0401, U10, I've got U codes coming out like all get out, and I also has a PCM code. So if you don't understand electricity, if you don't understand how circuits work, you're not going to fix this. So critical electrical skills will help us. Electrical electronics, we'll just look at this. So if we're looking at some other information up here, Ohm's law review. Voltage is electrical pressure. It's the pressure being in the circuit, and it's caused by movement of electrons in a conductor. Now, as we go through the circuit, the voltage will drop from the source voltage. We will use the voltage up. Okay, voltage provides a potential to do work, just a potential. The unit measured for electromotive force is volts. From all the guys had their name on it, you know, Volta, he came up with volt. Amperage is the work being done in the circuit. Amperage is what's being done, the work, and amperage will be the same throughout the circuit because it's providing a bit of work. 1 volt is the amount of pressure required to move 1 amp of current through 1 ohm of resistance. You've heard that a lot of times. And if I was looking at this next screen up here, one of the things I always tell everybody, a lot of times when you're looking at the nice little ohms charts, that kind of confuses some text and out there, because we don't use the word intensity. We don't use the word I for intensity or R for resistance sometimes. We don't definitely use the word E, but a lot of us have to realize that that is how the law was written. But we can also use, as you see on this little review, we can go back and say, hey, let's back out of here. We use volts, amps, and ohms. Same process. This is the Ohm's law that, you know, we got the fat little guy going through the center, and that's resistance. And we're going to kind of move him across. So let's look at something else. This is what I do when I'm teaching. I go back and it's usually E over R times I or whatever, you know, is there. So I convert it over. If you want to do this, it's not a problem. IFX, I teach a lot of text and I have a better idea of what's going on. So volts is also what we have for E, R is there, resistance, and I is for intensity, and that's for amps. Whatever way you feel comfortable doing it, this is what we need to look at. Now, my next slide up here, Ohm's law key relationship points. What I want you to understand, if the voltage is the same, and I'm just going to hit this one up here. You're going to see at the top, I've got here. If the voltage is the same and the resistance goes up, the amperage will always go down. More resistance, amperage will go down. Another thing about it is if you have a light in a circuit, more resistance in the circuit, the light will get dimmer. That's how you know that there's less amperage flowing through the circuit. If you look at the voltage is the same, but the resistance goes down, amperage will always go up. And if everything's the same, there will be no changes in the circuit. Now, if you look at what I've got here, sometimes we have the voltage going up or down. It can change, but most of the time in the automotive, we're going to stay with these first three at the top. Now, parts of a circuit, and most techs, including me, when I first came out, I took college electronics. This is when we used to use rocks to start cars. If you do part of the circuits, we have a source. We have to have a source voltage. That's your battery. Can we have source voltage coming from your PCM where we have a 5 volt coming out? That happens all the time where we feed 5 volts to the sensor. But if the battery's not good, we're not going to have a good output out of our computer. Now, we have to have some kind of protection device, whether it's a fuse or a circuit breaker or a fusible link somewhere down. We have to have some protection. If we don't have some protection in the circuit, we're going to probably go to short to ground. And that means the amperage is going to go full bore because of what? The last thing said, if the resistance goes down, the amperage goes up. We have to have some kind of control in the circuit. So we have to have some kind of switch or a computer control, something like that, doing our jobs. And we can have load or loads. All right, so we can have more than one light load. On this circuit I got up here, we only have one light in the circuit. And if you look at a process, I'm going to see if I get my highlighter back here. Oh, my laser pointer will be a little bit better. If you look at this one, I want to make sure you see this is a ground signal here, but also notice that on most cars, your body is going to be part of the ground. So that's a ground circuit going back to the battery. A lot of times we have issues. Your problems you're going to have on cars are usually going to be connections, or it's going to be on the ground, I see a lot of issues on the ground, and we'll talk about as we'll go through. But your ground is your return path back to the source voltage. And we also have wiring. And while we're here, if you're doing wiring on a car, I want you to start checking as your own reference and see how they want the circuit repaired. Because I'm noticing in some cars, they don't want us soldering anything. They want us to actually use special crimp wires up here and crimp a wire in place, which I just did a VW, had to crimp a bunch of wires there. So those are the parts of the circuit. Now, go to my next one up here. This is what's called a current track wiring diagram. But in a sense, I'm going to use an electrical board, and it works very similar. Battery power, if you're working on electric cars, battery power if you work on European cars, will always be 30. That's the unswitched battery. If you have switched battery, always be 15. And if you look at this one, I have switched battery. I have power going through a circuit, going down this and doing my operation up here, turning something on and making it work. And my ground is always going to be on 31. If you work on European cars, you need to understand those three wires. But we're working on the same principle here. The other thing is your wiring diagram is your roadmap of how the flow of electrons is moving through that circuit. So if I know for this circuit, I've got battery power up here, and I'm going to work through a switch and doing other items. So we have to look at our circuit in relationship. Now, the advantage of using test boards like we're going to is you're going to see the complete circuit. When you're working on a car, you're not going to see the complete circuit. So that's why the wiring diagram is advantageous for you to use to know where you need to do your probing for the easiest method. All right, electrical faults. Can we have an open? Yeah, we can have an open anywhere in the circuit. I have an open on the power side. I can have open on the ground side. I can have an open on a connector, which has happened quite a bit. We can have short to power, short to ground, or components internally shorted. Any of those things will happen. That happens a lot. And then we have high resistance on the ground and connections. A lot of you guys out there have heard of Stabilent, I'm going to say it wrong, I always do 21A. And when you clean up a connection, you put there to make sure it works real good. We also have an issue on some General Motors cars of the thing called fretting. And fretting is where there's micro resistance inside the circuit. So a lot of times when you disconnect and plug it back in, that circuit will start working. Well, you almost know for a fact it's going to be back later. So that's a connection issue. You can look up on General Motors, you'll see some issues on that. I've had some injectors where I've taken them off, they'll work for a while and then stop again. So those are connection problems we might run into. And there's 3 steps of circuit testing. I don't care what circuit you're looking at, you still have the 3 circuits. I have to check my voltage supply to the circuit. That might be my fuse. That might be right at the battery. I need to check the supply voltage before the load and check for any voltage drops. So I'm allowed a couple of tenths maybe going through, and depending on how many components I've gone through on my circuit, I'm going to not have source voltage if the circuit is live and it's working. So keep that in mind. Then what you want to do is check the voltage after the load. Now, when you check the voltage after the load, you're actually checking the ground circuit, and you're checking for any voltage drop left over on the ground circuit. It should be less than, a tenth of a volt on a 12-volt circuit, and the circuit must be closed and working. You cannot test a circuit properly with the circuit turned off. A lot of you are out there using ohm meters. Ohm meters work great as long as there is a spec. If there's a spec for it, then we test with it. An ohm meter also gives us continuity, but the problem about it is I can have a wire with one strand of wire there and still have continuity. So again, it's always best to check with the circuit working. If you go to a lot of diagnostic techniques and whatever, you'll always tell you the circuit has to be working to do our information. Now, voltage checking, we're always going to check in parallel. That means whatever, I'm going to check the voltage, and wherever I'm putting my black lead to ground, I'm looking at that. We're putting my black lead to ground somewhere, and I'm going to check voltage up here. All I'm reading is the amount of voltage available at that circuit right there, and I'm going to measure it on my meter. And the reason being is I'm supplying a pathway to ground for that. I'm bypassing everything. Since we have a really good meter with 10 mega ohms or more, that means I'm not going to affect the circuit. if I start affecting the circuit when you hook up your voltmeter on it, you need to get another voltmeter because it means the impedance is there. You can check the impedance on a meter if you take 2 meters together and you put one to voltage and one to amperage, one to check a diode, you can actually check the resistance back and forth playing around with your meters. But if we look at this next one up here, there's 2 types of voltage testing we always need to think about. First one, open circuit voltage. That is available voltage to the point you're testing with no current flowing through the circuit. Excuse me, I get a drink there. It does not allow testing resistance in the circuit. And so another way, it doesn't allow us to test for voltage drops in a circuit. A voltage drop is usually related to a resistance in the circuit. Okay, voltage drop is only done with current flowing through the circuit. It will indicate a drop in voltage because of connection. Now, when we see a drop in voltage, that means that component has consumed that voltage. It's a resistance there, and it's consumed the voltage, so the voltage dropped. Indicated drop connection, wiring, load resistance problem, either on the power or ground side of the circuit. So that's voltage drop testing. Let's have some fun with this so that go across. This is just a thinker on here. I have a lot of people, especially a do-it-yourselfer, will come into your shop and he says, well, my battery's good. All right, let's have some fun here. Open circuit voltage. Nothing's working in his car. The computer's in the background, but it's pulling minor little voltage. So I'm looking at this and it says I've got 12.02. It's a 12 volt battery. That should be good, right? Well, we'll see. If I take the state of charge as battery voltage or state of charge, open circuit voltage, state of charge up here, a 12 volt battery should have 12.7 volts, 12.6 volts on a fully charged battery. So we're at 12.02, indicates the battery is under 50% state of the charge. Do you want to start doing electrical testing on this vehicle? The answer is no. You want to make sure you're going to postpone your electrical testing till the battery's fully charged. Are you going to probably put a jump battery, or you're going to put a battery charger on there somewhere and do your testing? The other suggestion I make is, I don't know if you have a CAN breakout box where you hook it up in a DCL. Well, those a lot of times have voltmeters on them, and they will actually start squawking if the voltage is too high or too low. I was working on a circuit the other day and all of a sudden getting some funky readings on it, and all of a sudden I heard the nice little beeper beep on my CAN breakout box. You can get those from a whole bunch of different people, reasonably cost. It started beeping me. I was under 11.3 volts, so that means I needed to go back and charge my battery and start all over again. Let's try something else here. Okay, this is open circuit voltage. This circuit is open, there's no work being done. And if you look very careful what I've got here, I put a little bit of black paper behind this because when we're doing video, you can't see this, but if it's right in front of you doing a class, you'll be able to see it. So I have a 12 volt bulb there and a 12 volt bulb there. Neither bulb is lit right now, so I have whatever's available at the battery. So I have 12.67 volts. That means I have an open circuit voltage of 12.67. I'm not doing any work, so that would indicate, and I'll show you a little video in a second what it indicates to you. Now, we have some more fun of this one. Okay, voltage drop. All right, what I've got up here, if you look at right here, you will see there is a little bit of a light. You see the light is on here and there's a light on here. They're dim. Why are they dim? Well, that's because I have 2 bulbs. And 2 bulbs in it, they're going to share their part of the source voltage. And these are the same resistance, so they're going to be able to take half the voltage across. So across here, light bulb load is used at 6.1 volts, dropping supply voltage. Now I had battery voltage here, and I had 6.1 here, and then I had 6.02 or whatever and drop across. So the components consume the voltage in the circuit. That means when I start over here, I got 12.67 like my last slide did. But when I go down to this one, I'm going to have less than that. So just something to keep in mind when you're looking at circuits. All right. If you're using I'm going quickly here. I don't mean to do that to you guys, but 12 volts, maximum allowable voltage drops. All right, notice it says 0.00 volts across the connection. You're going to find out that you're going to see connections with a sizable voltage drop. Sometimes your relay, I tend to activate relays and see what my voltage drop across. I had the other day, I had one with a 1 volt drop across the relay. No wonder the circuits weren't working properly. 0.2 volts across a wire cable. It's like if you were testing your battery. You've all done the battery voltage drops, testing your battery or your charging system. 0.3 volts across the switch and 0.1 volt at a ground. What I'm giving you is a list of values. Now the values of here are general in spec. If you do not, in your service manual doesn't list voltage drop specification, use these to get an idea for you to do your diagnosis. So if all of a sudden I've got a 0.1 volt drop across the connection, I know immediately the connection's got corrosion on it, or it's bent, or something's going on. I need to clean that and retest, or I need to replace that component and do my testing. All right. Measuring current. Current is always with a voltmeter. We are always going to move our lead over down. You see that where we're moving our lead over with the red. And if you're doing the red up here, you see this one, we're moving our lead from here to here. Now the advantage of that is we're going to set it up for another circuit. Some of the meters will actually prevent you from putting it in there till you dial the right thing on your gauge. Measure current. The leads need to be moved to a correct position. The current needs to be in series with the circuit. The only exception to this rule would be if you're using an amp probe. But most of the testing that you're going to be doing, if you're verifying sensors and circuits, will probably be using your DVOM. Your DVOM plus your scan tool should always be there. And by the way, you buy a good DVOM. If you're going to spend money on anything besides a scan tool, your DVOM is your first choice. And you might want more than one because sometimes this happens. I'll show you real quickly. And sometimes other things happen. And I can't get it to go to my next screen. All right. You will get this. And those fuses blow a lot. I've gone to places where I keep an extra set of fuses. And if I share out meters, I will always have somebody blow a set of fuses for me. Those are expensive. Some of you will actually put a fuse in your line when you're testing it in order to protect it, where it's a fast blow fuse. You're only looking at 10 amp on that circuit with a DVOM. You can look at bigger when you're using your nice little amp probes that you can use to do testing. All right, let's go over to this one. If you're measuring resistance, you're always going to be what? Connections in parallel, or is that series? It looks more like you're just going to go across it, doesn't it? Components in series, remove. If the component's in the circuit, remove the component to test. Do not do what I used to do all the time, have one lead hooked up. Remove it from the circuit and test that component. If you don't, you're going to pick up other things in the component going down. If it's on a circuit board, there's times when I've had to repair computer circuits in some cars. I've had to remove or desolder one of the leads to actually check things. And the last thing up there is the most important thing. The circuit must be off when you use an ohm meter. Continuity, I was telling you that before. One strand of wire can still give you continuity. So the measuring resistance, the circuit must be off. Okay, we're going to look at something different. I'm going to switch angles on you and try this. Kirchhoff's circuit rules, series circuits. The total current is the same at any point in the circuit. No matter where you break into that circuit, the current flow is going to be the same. Pick your easiest spot. Don't work hard. If you're looking at a circuit, we call it lazy man diagnostics. Lazy man diagnostics will find the easiest way to get the information we need. And that works really well. The sum of the individual voltage drop will equal the source voltage. So in other words, if I put a circuit and I put my red lead on one side of the circuit and my black lead on the other side, I should have used up all the current in that circuit. We'll show you a little trick here. The sum of the individual resistance will equal the total circuit resistance. Those are just rules. But if you go, but I told my techs that come to class with me, I tell them actually take the Ohm's law and the Kirchhoff's law here, I probably say it wrong, and kind of put them in a little binder somewhere down the line as a reminder, because you're going to need these eventually. This is a series circuit. Now, this is really a good circuit, and if you're looking at what we've got up here, I've got my power supply here, positive and negative. Down at the bottom, remember I said it's similar to the circuit, the current track circuit. This is my ground. All my power is up at the top. So I feed in here. I have a circuit breaker right here, and I go over to my switch. There's my control device. And can I have resistance across this? You better believe I can. Then I'm going to go over here, and when I'm going to go through this bulb, notice I'm going through this bulb over to this one. They are now in series. So my 12-volt circuits are my two outer ones, and I'm going to go here to ground. That is a nice series circuit. Now I have two loads. Remember I showed you the voltage drop is 6.1. The main reason was I had a 12.2 circuit, and I was looking at differences going across. That's a series circuit. So here's an example of a series circuit. You won't find a lot of series circuits on cars anymore and trucks anymore because they're getting more and more complicated. This is 2010 Ford Ranger interior map light. And I'm going a little quickly, but I wanted to make sure that you see it's hot at all times. Hot at all times. I have a fuse F13 is 15. If you ever work on a Ford, you know finding the right fuse is one of the hardest things in the world to do, because they number things. They don't show you what they do. They give you a number. You have to look up the idiot sheet, or what I call the cheat sheet, to get the information. Now, if you notice something, I'm feeding off of this circuit to a switch here. A switch will be open. Yeah, I'm going to turn the map light on or off. I have a little switch there. But I have voltage going from the switch here. I'm going down through my wire, my connector, and I'm going down to the nice little component. It's got a little light in it, and there is a symbol for a ground. And you'll notice in some of your wiring diagrams, they're changing the ground signals as we're going through. I've noticed that General Motors has been changing wiring diagrams a lot lately. All right. So I have one load in this circuit in their process. Now, this is one I've just recently had a little problem with, and I'm just going to show you what we had. Most of you, the minute you see this, are going to say, I'm not going to do all that voltmeter test, Jim. I'm going to use my amp probe. That would be my first choice. But when I have a problem with this circuit, then I'm going to have to hook up my voltmeter and go through the circuit and look at things. So I have two fuses being fed over here. I also have a nice fuel pump motor diode right here. And you notice I'm going across my relay. There's your fuel pump relay. Battery junction there, and this is hot at all times as F06 is 20 amp and being fed through. This is my circuit. When the computer activates that circuit, by closing it, I should have voltage going down through the circuit to my neutral safety switch. And if you notice, these are how we're going to control to make sure it's working, and flowing over to one side of my fuel pump. And then at the other side of my fuel pump, I already said I should have less than what? A couple tenths of a volt. Now, out of curiosity, I just did one. And by the way, you definitely need to check these connectors on these cars, because a lot of them are melting on some of these cars with amperage on it. And you'll see a lot of fuel pump manufacturers are actually giving you a new harness that you have to hook in. Make sure you correctly hook it in. I have one, I had 4 volts at pin number 1. If I have 4 volts at pin number 1, what does that tell you? I've got a ground issue. So I'm following my ground up here and doing a voltage drop, and it's over here. This goes to the frame on this particular vehicle. I have had like 5 or 6 Ford 6.7 liters. All I've done is taken this off, clean the ground, putting it back on, and my problem with my fuel pump goes away. So that's why I'm going to, if my system's not pulling the right amount of amperage, I'm not getting the speed of my pump that I want, because some of you guys will get into that, I would automatically start by using my voltmeter down at the fuel pump wherever I can get. And that's not always easy to get to a fuel pump. I guarantee you that. All right. Here's my series circuit again. We're going to go over and try something different. Well, I did this class once before, and somebody had a little problem with it, what I did. And I want you to see up here. First of all, notice my light is on brighter right here. and I have one light in the circuit. So if I'm doing this, I'm going to play this up here, hopefully play this. All right. So if you're looking at my voltage right now, I'm going to check this circuit out. And I'm taking a little time to do it, but if I'm checking my circuit out, my ground's good. And I know you can't hear me up here, but I should have 12 volts going to the circuit. All right, there we go. So I have 12 volts going in, and I have 0.09 coming out. I used up the source voltage in this circuit. I didn't check my source there, but I know that. Now, if I hook this up into a series circuit, and the series circuit is there, and I have to do a little bit more here. I think my daughter was in the background while I was talking to her, something about her wedding coming up. Notice most of my bulbs are dim right now, but I'm going to have my 12.31 volts. I got 6.1 afterwards, 6.14, and that's a good circuit, but I have two loads. Why is the bulbs dim? Because I have to share the 12 volts across two. The bright light, I use all the 12 volts. When I have two loads in the circuit, I'm going to have to share my load. If I had three bulbs in the circuit of the same resistance, I would have 4 volts in each one of those. And if I had 4, I'd down to 3. They wouldn't be working, but that's what I'd have. So in other words, you keep that in mind. You can have 1 load or 2 loads or 3 loads in a circuit, but they will each use up so much voltage. So that's why I was doing the voltage drop. Okay. Here's a good series circuit. Let's just see if this one works out right for you.
Okay, check the supply voltage.
There's my supply voltage is 12.64.
Form a circuit breaker there.
And then after my circuit breaker, I have 12.4. So I've lost a little voltage. It go before my switch.
3. Plus the switch.
And I dropped it again. I dropped voltage here. And we're allowed 300, which I'm within reason. 5. 16. Right to that point. Use voltage there as my load. 6.
After that, 0.06. So it indicates we have a good circuit.
This is a good circuit. Now, while we're here, this circuit, if I was checking amperage, it's a live circuit. It would be different. Some of you are out there calculating what the amperage should be in a circuit. You got to keep in mind is when a bulb is turned on or a load is turned on, it's going to take some of that voltage away and change the amperage of the circuit, because on the light bulbs is actually going to go up, the amperage would increase. So you're looking at something a little bit different. Now let's try something a little different here. Go to my next slide. This is the series circuit. Let's have some fun with this one.
I inputted up.
There's a code set in this particular thing up here, a problem. Now both bulbs are out.
Light bulbs just went off.
Okay.
We're going to go ahead and check, but we don't have to go through all this. We know, but let's go ahead and check again. So I have
168 is my source voltage.
12.68. No, we go. Let's just make it easier. We're going to cross the switch.
12.68.
12.68.
12.68 again. 8 again.
Right now I have at this point. I have no voltage drop anywhere in the circuit. So this would indicate I have open circuits. I go to here, 12.68.
So that indicates that we got an open circuit
This component, take this, move it
here.
touch here.
Yeah.
So I know I have an
Open.
between
These
those
are
two
two.
components right there.
All right, so that shows you have an open. Again, if you read source voltage of the battery through the circuit, that indicates that you have an open. That's when a lot of us have been using voltmeters and going through the circuit. And I don't know if you can do that. I can't do it. There used to be, Jim Linder used to do a thing called Bubba test with light test lights. But a test light will go through the circuit. It will not tell you that difference of 0.4 of a volt. It will not tell you that difference of the circuit is actually live and working. That's why it's always better to use your voltmeter to check a circuit. It's always easier. You can use your test light if you want to, But when you think you have an issue, always bring out your voltmeter to do the final testing on it. All right, let's try one more here. All right, series circuit again.
Supply voltage of
12.67.
Again, 12.67. So I know I should have 12.67.
Before my 1.65, I dropped a little voltage. Dropped voltage against my switch.
And my first bulb up got
12.6.
After my
first bulb, I got 12.6. 0.36.
You go to this bulb here.
0.36. And after I got 12.15.
What does that indicate? It indicates I have a high resistance between this component here and this component here.
What usually happens at this point, we have high resistance at that point. You're not really going to not see that high, but it does happen sometimes where you have bad ground on something, bad wire. The biggest thing about it is, if you notice, I had source voltage before, open circuit voltage before, and this time I had 12.15. I do know the work was being done in the circuit, but I do also know I have high resistance. There's high resistance in a process that I won't turn my lights on. So you have to be careful again and look at your voltage and relationship. I should have, before my load, I should have 12 volts. If there's one load, after my load, I should use it. I shouldn't have any leftover voltage. If the voltage is not source voltage of the battery or source voltage of that circuit, then that indicates that I have an open circuit. On this one, I have a lot of resistance left over. A lot of voltage left over, so I know I have a high resistance on the circuit. It's just showing you that this is here. Now again, if I was on a car, I would have to use my wiring diagram. I have a friend of mine that actually uses a board similar to this, and what he does is he goes out and creates the wiring diagram, again, how the flow should be going through the circuit on the board. The reason he does that is that way he gets a good idea where he needs to go test in the circuit. And again, you're going to have to pick and choose what easiest way to test on your circuit. So let's try something again. If I was doing current testing, I'm at the top. I'm going from the battery to before my circuit breaker. I'm reading 169 milliamps. Good reading. I've got a completed circuit. I'm doing work. If I go to my next slide, I'm from the ground. Notice again, I'm from the ground on that sensor, on the ground side of that circuit to ground, and I'm measuring the amperage. I jumpered in series with it, so I jumpered at the output of the circuit at the bulb and to ground, and I got 169 milliamps. So that tells you right now, no matter where I should check the circuit, the amperage would be the same. But what changes? Voltage always changes. Amperage stays the same. So that's something you need to keep in mind when you're doing your testing. All right, let's look at some other thing, Kirchhoff's rules again on a parallel circuit. Voltage is applied equally to each branch of the parallel circuit. Good, we need to do some work there. The sum of the current flows in each branch is equal to the total current flow of the whole circuit. Total resistance of the entire circuit is always less than the lowest resistance in any single branch. These are what I call practical applying of the Ohm's law. So let's try something up here. So I have a parallel circuit. If you notice, I have battery power going to my circuit breaker. After my circuit breaker, which is most cars are feeding this way, I'm going to come off with one circuit that's in green, and it's going to be able to activate a little horn. You better be glad it don't have the sound on, because it drives you nuts if you listen to it for a while. The other red circuit comes all the way over to my switch again. It comes down, and it's going to supply voltage to my to my bulb. And you can move this back and forth. I didn't change the circuit, but it's what it looks like. Now, to have some fun with this one, here's an example. This is a parallel circuit example on backup lights. Now, I'm going to ask a real quick question for you. Think about this. If I was short to ground on one of these lights, if I short the ground here, what would happen to the lights? Well, it's going to be a little brighter up here. We're going to actually show changes in the circuit. Let's try something again. Let's go this next one up here. If you're doing parallel testing, all right, if you notice that what we've got up here, I'm hooked up into the voltage lead and I'm doing the circuit. Let's just see it. I'm doing a parallel test right now. I'm looking at the supply voltage, each one. That was open circuit voltage, was the one before here. It's 12.65. So I know I'm doing work because there's a light on. All right. And there's 12.52 at the switch. So that's adequate voltage. That's what I'm going to have at the switch. If I go over to my other circuit, which is on the other side, notice I have 12.52 volts. So each circuit has the same amount of voltage, 12.52 volts. Now I'm sharing it because what I'm sharing the source voltage, but I have two separate circuits because at this point they're parallel and they have their own grounds. So I can actually apply voltage to two circuits to make them work in two different things. A lot of you older technicians will remember the 2.8 or 3.4 General Motors, or excuse me, 2.8 General Motors V6, where they had gang fire. So we have one bank injectors would fire and the other bank injectors would fire going across. Again, that was a parallel circuit. So we could actually calculate by using amperage on that circuit and voltage. The voltage would be the same. The amperage would actually come up and tell us if we have an issue. All right. In parallel testing right now, so I'm looking at the point. Let's see if I go up here. Let's do this one. Parallel testing. I have all the circuits work. You notice my light's on down here. My button's on the little, my finger's on the little button here, so I have completed the circuit across this buzzer to ground. So I'm reading 270 milliamps in this particular circuit. All right. If I want to go over here and do this again, I have 250. If you notice, I don't have this other circuit activated over here, so my amperage right now, because that's not working, my amperage just dropped to 250 milliamps. So that bulb's pulling 250 milliamps through that particular circuit. Now, if I go out and just push the nice little lead there and turn off my light circuit, I'm now reading 21 milliamps. So that's how we get our circuits. There's two different circuits. Each one has amperage. When you add them together, you get total. So if let's just go back up. Adam's 270, that's 250, and that's 21. So you add them together, we're right there. We know what we're looking at. All right. And I'm going to get out of the time like I always do. Kirchhoff's rules, series parallel. Now, why was I doing series and doing parallel? Because here's a simple thing. The series portion of the circuit follows the series rules, and the parallel follows the parallel rules. So if I have, let's go back a few years where I wanted to dim the lights in the dash. It used to be we had a resistor up there. That was a series circuit where it went through a resistor, and that would go out to a parallel resistor, a parallel circuit, excuse me, and we power our lights up. So I actually can dial the lights up and down. Now we use it with computer circuits and a lot of other things. But a long time ago, we would actually dim it by using a little resistor. We also can use other things going in the process. So let's look at a series parallel circuit. And if you look, there's a lot of things going on in this particular circuit. And they're using a lot of resistors. Again, there is my series circuit. Where's it coming from? Again, my protection device, and it goes over to this resistor. Then I split it off at this resistor. So this is my series side. This is my parallel side going across this way. So that's why we do that. It makes it a little bit easier. Okay. If you were using one of these boards, if you thought it was crazy before, this is the taillight brake circuit, and you're looking at the brake switch, the headlight switch, and everything else going on, and you're looking at all the particular circuits in here. There's a lot of things going on. So again, this is designed to teach students. ATEC has come up with some way of actually teaching, having the shops themselves be able to teach electricity with some boards that you can look at. Now, I added a couple of things in from Monday. I actually added 3 things in from the class last time I did it. So I wanted to go to this next one up here. A lot of you are going to 2-wire circuits. You see it like a coolant sensor. Well, if the coolant sensor on your car reads 255, or if it reads, -40, that means it's either open or shorted. But here's the big deal about this. If you're checking a 2-wire circuit, the best way of doing this is actually taking and checking the voltage supplied to the sensor itself. So you disconnect it and supply voltage. Use a yellow and black on your motors, always remember it. You should have maybe 4.8, 4.9 volts. And if you would go in there with a tool number J1939, which is my tool called the paperclip or a jumper wire, if you jumper this, all of a sudden now you would see the voltage drop because it goes across the resistor is being used and flowing to ground. All right, so this is a process. Here's a reason. You can have some computers that are going to put in substitute values up there, and a lot of times you need to go out and check the circuit properly. So again, there's 2 wires. You're going to be able to check it out. Now, if we're looking at this, you're going to make sure your scan tool reads. And the other thing, you can check the scan tool's ability to read the circuit. Remember, it's interpreting what data it sees. So if I disconnect it, it should go what? It should be open. Okay. If I short across it, it should be shorted, so the voltage should change high and low. The big idea for you to do this is make sure you use this in conjunction with your scan tool. Now, if I was going out to my next circuit, it's 3-wire circuit. We have a ground, we have a reference, 4.9 to 5.1 volts, and we have a reference. This happens to be a TPS sensor that we're looking at, and it's variable resistance in it. So most of the time, the computer is going to monitor which part of the circuit. It's going to monitor the return voltage to the computer. It doesn't know what the ground is, and it doesn't really know what the supply voltage is. As long as the circuit is complete, it's going to pass it. So I sometimes have people put new sensors into vehicles, and when they do that, they end up with an issue. And the issue they end up with is they didn't check the power going into the circuit, and they didn't check the ground. Now, the other thing, if you're looking at this, you go back to your wiring diagram, keep this in mind. That ground might be shared with 4 or 5 other sensors, or at least 2. It's usually always 2 that share the ground. This reference voltage might be on 1 wire, and it might be feeding 3 or 4 different sensors. So if one is shorted, it's going to affect the rest. So a lot of times what you want to do, if you have issues with voltage problems here or here, the input or the ground, by the way, if this is messed up, it will definitely mess up the signal going back to the computer. If I'm missing 5 volts, it's going to mess up the voltage going back to the computer. So these are things you need to take in a process. And a lot of times, I've seen people replace sensors when there's nothing wrong with it. It's just a bad ground wire. Older General Motors used to ground some of their sensors at the thermostat housing. Corrosion over a period of time. That's why sometimes you want to clean something to use Stablant 21A and make things work properly. So 22A, I always get that messed up. All right, let's try one more here. All right, if you got some questions, we'll answer those for you, but the big thing is I want to let you know that ATEC training up here, if you need to get hold of service or technical support, you get hold of Brian Jenkins. I'm James Wilson. You can get a hold of me at instructors@atectraining.com, and those are the phone numbers you need to look at. And Dave, do we have any questions out there?
Yeah, we'll be able to take a few because, time permitting here, we're close to the session. First one is what general cautions do you recommend? This is from Tom. What general cautions do you recommend when probing or accessing circuits?
Yeah, every time I have a class, that's the first thing. First of all, I recommend you don't pierce wires. I just recommend that at all. The other thing is you want to get the narrowest. I use the either T-pins from a drapery store. They look at you funny when you buy them, but that's okay. Or I use the AES Wave, or there's a couple other companies make these real thin back probing devices, or you can do it, you put on your voltmeter. I use those. The big thing about it is do not be shoving those things in there. Be very careful to slide it alongside the connector that you're doing. A lot of us go out there and push it in. If you want to look at it, connectors are problems. The other thing is General Motors has another thing you might look. I'm just picking on them right now. They have a little bit of a thing. They will tell you what size of it if it's got a round tube, you know, the male and female connectors, they'll tell you how big they're supposed to be. And sometimes you want to actually test those for drag fitting. You can actually take a drill bit that's proper size and check those for drag fitting. Make sure when you check in these circuits, you're not actually accidentally grounding things. I did some injectors one time, I popped them, it happens. But those are the precautions. And the other thing, if you have no other way to do it and you are back probing, make sure you put something on that to fill that hole in. The other thing is I recommend that you basically, anytime you disconnect a sensor from a circuit, you mess it up. Always back probe first, then if you have an issue, disconnect it, because by taking it on and off, you can maybe fix the problem. If you back probe, take it off and see you got a problem, put it back on, and you still back probing and it looks better, that probably indicates you have a problem with corrosion at that connector. Does that help?
I think we'll have to go with that. And then another one here. This is from Randy. What are your thoughts on using a jump pack or battery charger when doing electrical testing?
I would say it's a good idea. Jump pack is what I use. The other thing is I hate to tell you this, but I take that little can box that plugs in your diagnostic connector when I'm doing electrical testing. I plug that in and leave it there. And the reason being, if I have a loss in voltage, I pick it up. Jump box is a good idea on some circuits. Other circuits, it might cause an issue and overpower some things, so be very careful. If you're doing network testing where you spend a lot of time on it, I recommend you using a jump pack or the battery charger, and especially if the ones that you use to do computer reprogramming would be the better at that source at that time. Okay.
Okay, thank you. And then you mentioned earlier, James, that there are few series circuits remaining on vehicles. What are some typical circuits that are series?
You might have, it used to be the MAP series, the dome light. Nowadays, that doesn't even there. But if you come up with series circuit, it would be your, most of the time, the non-modulated fuel pumps are series circuits. Anytime you have some kind of module inside the computer or in line to the fuel pump, then it's modulated, it's digital. It's not a series circuit anymore. It's going to be controlled. The readings are different. Most fuel pumps, I would say, are your series circuits you're going to be looking at. Some of the light switches on some of the cars. The more inexpensive cars are going to still be using easy way to turn, you know, lights on and off, you know, door switches, whatever that might be your series circuits you're going to run nowadays.
All right, fair game. And then David would like to know about more information on no solder protocols.
Okay, here's the deal. On a lot of the European cars, I want you to go out and look this stuff up on your own. I want you to go out, if you go out to Audi and VW, or you go to a few other places, and they will actually tell you they don't want you to solder a circuit. The reason being is they have special crimp circuits that you can use. The reason they're looking at this is I don't know if any of you guys are out there into racing. And if you're into racing, I just started getting into building wiring harnesses for race cars, and as just something I wanted to do. And first thing I thought was crazy, they wouldn't let me solder anything at all. Solder connections get brittle. A solder connection can go bad, but what they wanted us to do is there are some, if you go out there, they're like open barrel or closed barrel sensors. They're crimp sensors where you actually took 2 ends of the wire and go in the crimp on each side, on the barrel each side, and you crimp them down with a special pair of crimp pliers. The reason being is if you do that, you know, you're going to be able to put your nice little protection on it, your shrink wrap after that. You can do that too, but the reason being is they think that by soldering it can create issues. The other thing is, the biggest thing they think is it can be a brittle connection, and that's the big issue. And they think some of the circuits we're going to have in the future will be really critical to the resistance of a solder circuit versus the actual being able to do a crimp circuit where you have a mechanical connection. If you notice a lot of the cars right now, you'll see that everything is bent over and connected. I advise everybody get a pair of crimp boy, I can't talk today, pliers, and actually go out and look at, crimping things. You will see a whole lot of information on how to properly repair things. I've worked on school buses and some of the buses, and the big things on them, they did not want their circuits to be soldered. They wanted them to be crimped, and they all had special techniques. You want to be able to start doing that as we go forward, because it will prevent a lot of issues. It's a mechanical connection. It is a tight connection. When you get done with one of those, you can't pull them apart. They're tight, and there's no resistance in it. That's the whole idea. Did that help? That's what I've been learning, and that's what I've been applying. I've just fixed a couple of circuits on a few cars where I tried soldering, and I had an issue where they broke later, and I went to the crimp, and the last one has been gone 2.5 years, so I haven't seen it. So the crimp is going to be the way to go.
Good recommendation, not to mention also the fact that oftentimes solder is relied upon as a mechanical connection, which it is not.
No, it is not. The other thing is, some people don't realize you have to use the right kind of solder also. Silver solder, and it has to have the rosin core, and a lot of times also on top of that, if you heat the wire up too high, you actually cause a problem, and by doing the mechanical, you don't heat the wire.
Yeah, good point about that. Any general view, James, on the use of dielectric grease?
Use it. Use it. You know what, I was talking to you about the fretting on the General Motors products, but they will tell you when you're doing this, let's say you clean a connection. I'm using all kinds of de-cleaning particular sprays up here. I forgot that. I can't even remember that. I just use it now. I forgot it. What you want to do is clean it as best you can, put it back together, and use dielectric grease. That way you're preventing the air from getting to that connection. If you prevent the air from getting to that connection, you're not going to have the fretting problem that General Motors has talked to. They've been doing this since the 80s, believe it or not. So what happens by preventing the air from getting to that connector, you're going to prevent the corrosion from building up inside. It's micro corrosion that you're looking at. So yeah, dielectric compound, I use it to fill circuits, at the connectors. Just make sure when you put them together that it actually clicks together. I had some guy put so much in there it didn't click together. Remember, Ford used to tell you, and you guys are too young to remember this, but Ford used to tell us that, if you didn't hear the click, it didn't work. So again, dielectric compound keeps the air from getting to it, keep air from getting to it, and moisture can get it to you. You're going to have a better connection. It's going to last a lot longer. I believe in dielectric compound, yes.
All right, that's about all the time that we have, folks. So I want to thank James Wilson for his presentation today. Gave us a lot of insight, and James got a lot of feedback in the questions pane, a lot of high fives there, saying thanks a lot for the information that you provided today. Of course, there's a lot of questions outside the scope of this presentation that were presented that we just can't get to today, and I encourage the audience today to take Jim's contact information and contact him about things, again, outside the boundaries of what we're really talking about. So the final note to the audience, to watch for a follow-up email coming within a week that will have a link to your certificate of attendance and a link to the recording of the session. Many people were asking about, a PowerPoint or a copy of the presentation. The answer to that, once again, is no. There is no copy of the presentation. However, you get the next best thing, and maybe it's even better, which is that you can go back and watch this in video format, stopping, rewinding, starting over again to reinforce those points that you need to go over uniquely for you, because some people are going to be more interested in one part or the other, but you'll be able to go through that at your pace, at your convenience, to be able to get the most out of this session. So thanks again, everybody, for attending, and remember to watch your inbox for future invitations for these sessions. Want you all to have a good weekend, and we look forward to seeing you at another session soon. Thanks, everyone.
Thank you, guys.